Hello again. I'm going to try to show you how to do internal standard setup and calculations. Internal standards are superficially similar to standard addition, but it isn't the same. It's used a lot in gas chromatography and other sorts of places, but what you have instead of added analyte, you have some other standard material, we'll call it S, and it'll have some peak area. You can figure that that's got some area. This is area of X for some unknown concentration of X. And there's S. Especially in the old days of gas chromatography, your injection volume would be not easy to reproduce properly. You might have detector variability. You might have losses during sample preparation and so on. So there are a number of situations where an internal standard type thing is useful and necessary. And once again, you have a standard material that is similar to, but not the sample itself, not the analyte itself. So we first thing we do is we take standard material, standard analyte, and standard S, the internal standard, and you measure one or more mixed standards. There's a number of ways to do this. We're going to do it with a single sample that you would certainly want to replicate, but a single standard. Anyway, so we take our standard material and the area or whatever you want to measure of X is to the concentration of X, our analyte, as it's proportional to what you do is you ratio the peaks or the areas or whatever, and the area of the standard to the concentration of the standard. Now this isn't usually almost never exactly 1-to-1, so we have a proportionality factor that's called, according to who you're looking at, whose book you're looking at, F or R for response factor. And different people set up this proportion different ways. It doesn't really matter, but you got to be consistent. If you pick it this way, you got to do it this way. So first of all, let's plug in our numbers. So what we're going to do, let's go ahead and rearrange it to solve for our factor here. So we'll say F is going to be, we just cross multiply here, area of X times standard concentration divided by analyte concentration times the area of the standard. And in our case here, that equals 3473 times the standard concentration, 1.72 millimolar. So here we go, 1.72 millimolar analyte area, 3473, and then we've got our analyte concentration is 3.47 millimolar times 10,222 area. And I'm gonna, let me get rid of this so I can save space. All right. And so F equals 0.168. And I've kept way more sig figs than I deserve, but we'll leave those as subscripts. All right, so that's something we're going to need right along here. I'll underline that. And all righty. Now what we need is our, the next step, what we need to do, we now take a known amount of standard. So we got 1 mil of 8.47 millimolar standard. We took that and added it to 5 mils of our unknown. This is our analyte sample, but this is our unknown. And we diluted it up to 10 mil. So, and then we measured the peak areas. In this case, it was peak areas. So what we want, first, we need to figure out what is our standard concentration in our final solution. I'll put a subscript there. And so we had, what was it, 1 mil times 8.47 millimolar, and we diluted that up to 10 mils. And that's 0.84, 0.847 millimolar. And again, that's S. All righty. Now, let me get a few things out of the way here. Okay. Now let's rearrange our formula. Let's our final concentration of analyte is going to be equal to, that'll be area of the unknown analyte times concentration of standard, that's the final concentration, divided by F, and then that should be the area of the standard. And we plug all that in and we get, so A of X is 5428. And S final is 0.847 millimolar divided by F, 0.16841 times the area of the standard, and that is 4431. And that turns out to be 6.16 millimolar. And once again, that's, let's see, that's the concentration in the final. We now need to take account of our dilution factor, so that our X initial is going to be X final times the dilution factor. That would be our final volume, divided by our initial sample volume. And that equals our 6.16 millimolar. And we started with 5 mils of sample and diluted it up to 10 mils. So our dilution factor is 2, and we end up at the end of the day with 12.32 millimolar of X. And that is all we need to do for the moment right here. So that's all for this one. And I will be back as we need to be in touch with each other.